Alrighty, so here I am. I'm going to show you how to solve the last free response that I assigned to you. And so this is the spacecraft A and B Unit 1 free response. And the question says that there's two spacecraft, A and B, and they're flying parallel to each other. And they're next to each other at time equals 0. That means that they're going to be at x equals 0 at time equals 0. And for the first 6 seconds, spacecraft A's velocity and spacecraft B's velocity are given by these two equations. One has a minus 5t and the other has a plus 3t. That's the big difference between those two. And both velocities are in units of meters per second. And then at t equals 6 seconds, the spacecraft are going to turn off their engines and travel at a constant speed. So they're going to ask us some questions. Part A. At t equals 0, is the speed of spacecraft A greater than, less than, or equal to the speed of spacecraft B? All right, so let's transcribe these two equations. The velocity of A is going to be t squared, there we go, minus 5t plus 20. And the velocity of spacecraft B is going to be t squared plus 3t plus 10. And they would like to know for part A, which of these guys is going to be going faster at a time of 0. So all we have to do is plug 0 into t for each of these situations. And that means that we just put in a 0 for t here, squared, minus 5 times 0 plus 20. So velocity A at time of 0 is going to be 20. And velocity B at time of 0 is going to be 10. Therefore, velocity of A is going to be greater than velocity of B. How did that work out? Okay, so then for part B, I'm sorry, the short pause is because I have a sheet of paper over here to my right that you can't see, where I solved for what was true at a time of 6. So I don't know what I did there. It's clearly asked about 0. There we go. For part B, each spacecraft has thrusters for speeding up and reverse thrusters for slowing down. At t equals 0, one of the spacecrafts is slowing down, the other is speeding up. Which spacecraft is slowing down? Okay, so in order to understand whether you're speeding up or slowing down, we need to find the acceleration of A and the acceleration of B. In general, acceleration is the derivative of the velocity. So we need to take a derivative of these things. That means that the acceleration of A is going to be the derivative of this function of A. So that's going to be 2t minus 5. That's right, you reduce the power by 1. Acceleration B is going to be 2t plus 3. So now let's put in our time of 0 and find out that the acceleration of A at a time of 0 is minus 5, and our acceleration of B at a time of 0 is plus 3. That means that this one is slowing down, and this one is speeding up. Now, when it comes to justifying your answer, you would say that A is slowing, and you could just refer to your mathematics above, if you'd like to, as the justification, or you could explain that you take the derivative, you set t equals 0, and that at that point A has a negative acceleration. Okay, so that's I, by the way. Now it says calculate the time interval during which the spacecraft selected in part BI is slowing down. Okay, now that we know that A is slowing down, let's figure out what's going on with A. When will it not be negative? When will the acceleration not be negative? So we have that the acceleration of A is 2t minus 5. I'm being distracted by this little hair on top of my pen. There we go. 2t minus 5. Now, we know that's negative at a t equals 0. When does it stop being negative? When does that happen? Well, that happens when 2t is equal to 5. And for every time after that, it'll be positive. So that is easy enough to figure that a time of 5 over 2, or 2.5 seconds, is when. So we have a time interval between 0 and 2.5 seconds is the time interval in which spacecraft A is slowing down. All right, let's have a look at part C. Now, part C asks you to calculate the value of t at which the two spacecrafts are traveling at the same speed. Okay, well, that's not too bad because we have the original functions. And the original functions, we need them to be equal to each other. We want the speed of spacecraft A to be equal to the speed of spacecraft B. That means we need t squared minus 5t plus 20 to be equal to t squared plus 3t plus 10. At this point, the t squareds cancel out on both sides. And I'll move this minus 5t to the other side and this 10 to this side. That means that there's going to be positive 10 left over. This positive 10 comes over here as a negative 10. And this negative 5t goes over there as a positive 5t, giving us 8t. That means that t is going to be 10/8. And 8/8 is 1 and 2/8 is a quarter. So this is going to be 1.25 seconds is the time at which the two speeds will be the same. Okay, we're good. We're through C. We have probably a good fraction of the points at this point. And it's time to get another piece of paper and to tackle part D. Let's have a look at part D. Part D says, is the acceleration of spacecraft A increasing, decreasing, or constant? Is the acceleration of spacecraft A increasing, decreasing, or constant? Okay, well, let's have a look on this page. Oh, Lordy, I threw it on the ground. On this page, we had actually calculated the formula for the acceleration of spacecraft A. And here it is. So let's transcribe this onto this other page here for part D. The acceleration of spacecraft A is going to be 2t minus 5. And we need to now opine about whether this is an increasing, decreasing, or constant function. Well, I look at this and I see the equation for a line. Y equals mx plus b. So the m is equal to 2. The slope is equal to 2. That is a positive slope, which means increasing. I don't know how you want to say it, but obviously this function right here, 2t minus 5, is an increasing function. It may start at minus 5, but it's increasing as time goes on. So that's a very easy kill there. Now here's where we get ourselves into a little bit of trouble. I've been through this a couple times, and the question says for part E, the following data are collected on the position of spacecraft A and the position of spacecraft B. Both spacecrafts are at position x equals 0 at t equals 0. Now, the fact that they mention spacecraft A and spacecraft B makes me think that the equation is still valid. But I have come to the conclusion that the equation is not valid. And the reason why is that we are going to plot this data. This is what part EI is. It says to plot the data. And if you plot the data, you are not going to get the right function. And here's what I mean. On our original function for the velocity, this is a parabola. It has a squared term. And now to get position out of velocity, it's not a derivative, that's acceleration. We need to integrate this. That means that our position function is going to have a t cubed in it. This is a very steep increasing function. And we're going to see that this is not what happens when we plot this data. So let's go ahead and plot the data. The data is listed here on this table. And I'm going to put the table off to the side. And I'm going to, I'm going to put the table off to the side. And I'm going to put the graph here. Now, we want to show the College Board that we know how to make a plot. So let's have a look at our times. Our times are going to be on the x-axis, and they need to be 1, 2, 3, 4, and 5. And here we have an origin, and 1, 2, 3, 4, 5. This looks like a natural to go ahead and make this 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds. So I'm going to label this as time in seconds. Now, we have the same 1, 2, 3, 4, 5 divisions going upwards, and we look now for our largest value, and our largest value is 129. This is a little bit problematic. I would love if this graph went to 100, and each of these is 20, 40, 60, 80, 100. But although that graph would leave out just this one point, I think the College Board would be unhappy with you just leaving out that one point. So I think what we need here is I need a graph that goes above 129. So let's see what happens. If we went to 125, we could do 25, 50, 75, 100, 125, but that's still not going to have this point on there. So I think we need to go to 150. Now, how does this divide up? How do you break this into 5 sections? Those sections would each be 30. So this is a bit odd, but I think if you did anything else, and I personally, as a scientist, would be perfectly happy leaving this point off, because I suspect that all the interesting information would be contained in the bulk of the data. And actually, if you zoom in and make a larger graph of the bulk of the data, you're going to get a better result. But hey, I want to show the College Board that I know some science, I know some physics. So I am going to make sure that I include all of those things. All right, so here's what we're going to do. Oh boy. Maybe I should just get rid of this. All right, so here's the deal. We're going to graph this information, and I'm going to graph spacecraft A here, and I'm going to graph spacecraft B in purple. Oh, you know what I didn't do? And this is probably worth points. I didn't specify that this was X measured in meters. Okay. So let's just put some identifiable dots for spacecraft A. Spacecraft A, well, obviously spacecraft A starts at 0, 0, and at 1 second is at 18. Now, 18 is going to be, let's see, this is 30. Oh my God, and we've broken this into 5, so those are 6 each. So 6, 12, 18. Okay, so we're right here. Good job. 2, 33. 33. 33. Well, each of these is 6, so we're halfway up. There we go. 3, 47. Okay, 30, 36, 42. 6 more is 48. 47 is just below that, so let's just put a dot right there. Okay, 4 is 61. Okay, we got 60, and then we're going to go 1 up at a 6, so that's barely perceptibly above 60. And then 5 is 79. 66, 72, 72 plus 6 is 78, and we want 79, so it's barely perceptibly above that. Okay, so these data look like they form a straight line to me, and since I know that they're going to ask me to go ahead and do this, I'm gonna put a straight line. Clearly, these are not an t cubed function. There would be significantly more curvature. So I'm going to go ahead and, why it looks like some sort of line like this would match this data. I've got some points that are above, maybe a little points that are below. Maybe my line's not the greatest line in the world, but dang it, I've done a good job, I think. Okay, time for B. B. At 0 is 0. At 1 second, it's only 12. That's easy because that's a below 18 by 1. 12 is 29. That's just below 30. Okay, 3 is at 53. 53. Oh my. Okay, so this is 60. 60 minus 6 is 54. So we're just above that dot. 4, we're at 85. 85. 90 minus 6 is 94. All right, sorry, 84. So 85 is there. And 5, we're all the way up at 129. 126, 129. All right, this does not look like a line at all. First of all, it's below the dotted line of A here, and then it goes above. So this is some sort of curving function that crosses through at some point. I've just kind of hand-drawn this thing, and I think, and this becomes important later, I think that our crossing happens right about here. In fact, let me circle that with a solid line. I'm doing this for you. I'm not sure you would need to do that kind of circling, but I've read the problem through ahead of time. So as far as EI, we've done a good job of making a graph here. Now we need to answer EII. And EII, and I've lost my my paper here that has the questions. EII. EII. Well, where was that thing that had all the data on it? Well, 1, E, I. Select a point value. Okay, hold on. E. Oh, I have so many pieces of paper here. EI. And where's the... It should be on the graph that I made earlier. There it is. EII. Okay, this is a graph I made earlier. EII says, at the point where the two graphs cross, is the speed of spacecraft A greater than or less than or equal to the speed of spacecraft B? Justify your answer. Okay, looking at this area here, we have an orange line at the moment that they cross that is like this, and we have a purple line at the moment that they cross that is more like this. Now, why am I indicating the slope? Because this is a graph of position versus time, and the speed is the slope. So it looks like B is faster because, or maybe I put the arrow that way, the slope is steeper at that point. It's not steeper down here. It is much steeper over here, but at that moment that it's crossing, it has to be steeper. I mean, it has to be steeper. You started below this curve, and in order to cross and go through it again, you need to be at a steeper slope. So those are all the answers that you need in order to get full points for this particular question. And if you have any questions about this process, please show up to office hours and ask me questions. All right, thank you so much.